Good afternoon and welcome back. So, we will begin today our 12th lecture in this series. So, let me just browse quickly through our last lecture where our work was dealt with finding initially the minimum distance of a chord. So, let me do this, and I told you that it is equal to the minimum Hamming weight. We proved that. We looked at examples, and then we defined an alternative means of determining the minimum distance using a parameter s, and we proved the theorem that d min is s plus 1. Then we showed that for the Hamming chord s is 2, and this also led us to define the general Hamming chord. Then we proved the singleton bound, which is a straightforward consequence of what we had done before, and chords that meet the singleton bound are called MDS chords, and we looked at 2 examples, and I quickly mentioned that there are no other known families. And towards the end of the lecture, we started looking at bounds on the size of a chord, and we started out with the Hamming bound. And what we showed is that the Hamming bound, we wrote down the expression of the Hamming bound, we did not actually prove it, and I just about got started proving this. So, what I am going to do is I am going to copy this page over here onto our next lecture. And I am going to, so this is lecture 12 as I just mentioned. And we are going to call this bounds on the size of a chord. So, just as a quick recap, we looked at we showed last time that d min equals w min, that d min was equal to s plus 1. This led us to define the we looked at examples, of course, and in both cases we looked at examples, and we went on to show we talked about the general Hamming chord, and we talked about the singleton bound, and MDS chords. And then towards the end of the last lecture, we were looking at the proof of the Hamming bound. So, the Hamming bound says that, let me just get rid of this extra page that I had introduced here. Okay. So the Hamming bound said the following: that the size of the code is less than or equal to 2 to the n divided by the sum I is equal to 0 to t n choose I, where t was defined as d min minus 1 upon 2. Okay. And we started proving this using the following argument. Now, so let me just erase this last part over here. I am going to phrase it if I can, that is. I am going to so let me just say it out in words, and then afterwards I will write down the proof. So in words, what it's actually saying is that if you look at the set of all n tuples, okay, then inside that set of n tuples are contained the code words, and around each code word you can actually define a ball of radius t, and these balls must also be contained in the set of all n tuples. But it turns out that these balls are disjoint, there is no overlap. So what that means is that if you count the number of code words, multiply that by the number of vectors in a ball, then that must be less than the total number of vectors, and that's where the Hamming bound comes from. Okay. So let's go down here. So f 2 to the n contains the balls of radius t centered around all of the code words. But these balls are disjoint, meaning that BCT is phi. Okay. So now we are just going to count. We are going to say that since one set contains the other, the cardinality of the first set must be greater than or equal to the cardinality of the second. It follows that that 2 to the n is greater than or equal to the number of code words m times the size of the number of vectors in a ball of radius t, which is nothing but okay. So from this the Hamming bound follows. Alright, so that proves the theorem. Now let's look at examples and see where we stand with respect to this bound, but first I need a definition. A perfect code is a code that satisfies the Hamming bound with equality, i.e. the size of the code is equal to 2 to the n divided by the sum over I and choose I. All right. Of course, a natural question to ask is, well, do perfect codes exist? So, example 1, consider the repetition code for odd values of block length n. Then you know that the parameters of this code are n, the dimension is 1, and the minimum distance is also n. Now, what does the Hamming bound say? The Hamming bound says that m in this case is less than or equal to 2 to the n divided by the sum I goes from 0 to t and choose I. Now, we know that if you add I goes from 0 to n, if you add up all the binomial coefficients, you get 2 to the n. This is well known. It is a well known result in combinatorics or from the binomial theorem. And when n is odd, since n choose I is equal to n choose n minus I, it follows that this is in fact equal to 2 to the n minus 1. Because there is a mirror symmetry between the binomial coefficients. So, if you sum all of them, then you get 2 to the n, but let us say you start from the left and you sum up to halfway, then you will get 2 to the n minus 1. Okay. So, that is what this is saying. So, now we are ready to plug this in. So, we want to use this and plug it into the Hamming bound. So, here is the Hamming bound. So, we want to replace the denominator here, we want to replace this denominator here with what we have just derived. Therefore, m is less than or equal to 2 to the n divided by 2 to the n minus 1, which is 2. Okay. Therefore, all such repetition codes are in fact perfect. Now naturally you must be wondering, well, how about the single parity check code, are they also perfect? So you can verify, I will leave this as an exercise, verify that the single parity check code is not perfect in general. Are there any other perfect codes? The situation when we were talking about MDS codes, I pointed out that the news is in some sense bad news, because the only known MDS codes are the trivial codes, which are either the repetition code or the single parity check code. In the case of perfect codes, however, the news is a little bit better. There is one family of codes that meets the Hamming bound with equality, and not surprisingly this is the class of the general class of Hamming codes. So the general Hamming code is always perfect. Okay, proof. Remember that the general Hamming code has these parameters. Parameters are n equals 2 to the r, k is 2 to the r minus 1 minus r, and d or d min is 3. Now if you check the Hamming bound, m is less than or equal to 2 to the n divided by the sum I is equal to 0. So here t is equal to 1. So 0 to 1, n choose I. So this becomes, by the way, there is a small typo here, n is not 2 to the n r, it's n is 2 to the r minus 1. So if you apply this, then this is 2 to the 2 to the r minus 1 divided by 1 plus 2 to the r minus 1, which reduces to 2 to the 2 to the r minus 1 minus r, which is precisely the dimension of the code. So therefore it's perfect. I should also say that the Hamming code, the Hamming bound is also known as the sphere packing bound, because you can think of a picture like this, where you have the code words and you have these balls of radius, spheres of Hamming t, of radius t, and these perfectly cover the space, they pack the space, in the sense that there are no vectors left over, that is, apart from the code words and the balls surrounding them, there are no other vectors, there is no empty space, so to speak. So, for this reason it is also called the sphere packing bound. Okay, so we have seen that repetition codes of odd length are perfect, then every Hamming code is perfect. So, are there any other perfect codes? And the story here is interesting. There is a coding theorist, Marcel Golay, who actually was pursuing the same question, and he made the following observation. He said, look, let us assume that there is a linear code which is perfect. Okay. Then he looked at the Hamming bound and he made a certain observation. He noticed that the sum of certain binomial coefficients had to equal a power of 2, and he said, so this is new, and then this gets into numerology, because what you are saying now is I am just going to look at numbers and see if I can get the sum of certain consecutive binomial coefficients to equal a power of 2. Once I find that, then I can actually start looking for perfect codes. It seems like a far-fetched idea, but actually it worked. So, here is what he did many years ago. So, this class of code is called the Golay code, and it arose from the following calculation. Supposing you take n to be 23 and you take d to be 7, in which case t is 3. So, Golay's observation was that, so perhaps since this is an aside, let me do one thing. I am going to let me introduce, I will insert a page here. Okay, so we will come back to the Golay code. So, let us put down Golay's observation first. If a linear code is perfect, then you must have that the size of the code must equal 2 to the n or in other words, the sum I is equal to 0 to t n choose I must equal 2 to the n minus k. So, this is what I was telling you about earlier, that is, his observation was basically that if you took the sum of certain the first few binomial coefficients, then you must end up with a power of 2, and so these are precisely the binomial coefficients in question. Okay. So, let us call this equation 1, and so he so his search for his approach to searching for perfect codes was to actually look at different values of n and then try to see when is it true that you can actually get a power of 2, and it turns out that it is not very often that this happens. There were certain specific cases in which it does happen, and then he was able to rule out the existence of perfect codes in some of those. This n equals 23 was a case in which he could not rule out the existence. So, then he set about constructing a code, and I think it's he was a brilliant coding theorist, and he did manage to come up back this many years ago, so many years ago, with a perfect code. So, equation 1 in this case will actually read like, so will ask us to compute the sum 23 choose I for I going from 0 to 3, which is 23 choose 0 plus 23 choose 1 plus 23 choose 2 plus 23 choose 3. Okay. Now, this is 1 plus 23 plus 23 into 22 divided by 2 plus 23 into 22 into 21 divided by 1 into 2 into 3. Okay. So, this is 1 plus 23 plus 253 from multiplying 11 times 23 plus 23 times 77. So, let us do that computation on the side. Okay. So, this is therefore 1771 plus 253 plus 23 plus 1. If you add it, you get 81402, and this is precisely 2 to the 11. So, that was his discovery, and that led him to consider the possibility that a code with such parameters exists. So, we will not go any further into this. So, this led him. So, this numerical calculation led Golay to construct a perfect code. The parameters of this code were 23, the dimension is 11, the minimum distance is 7. This code is now called the Golay code, not surprisingly. So, now this may actually lead you to ask to keep pushing a little bit further and say, okay, so now I know that the repetition codes of odd length are perfect. I know that every Hamming code is perfect, and I have just seen the parameters of a Golay code. Are there any others? And it turns out that there are no other perfect codes that are known. Although that took some time to prove and involved several coding theorists, including a Finnish coding theorist, Tietoväinen. So, that took longer to prove, but these are all the known, these are the only possible perfect codes. There are perfect codes other than this, but those are ternary, and they are also called Golay codes. To distinguish between the two, you call them the ternary Golay code, but apart from these, no perfect codes are known. So, that is as far as upper bounds on the size of a code. So, now let us turn our attention to a lower bound, and this particular lower bound is called the Gilbert-Warschauer lower bound. By the way, I think it is worth noting that the bounds that we are stating hold for any code, regardless of whether it is linear or not necessarily linear. However, the examples that are known are linear codes, which is interesting. So, theorem, and we will abbreviate Gilbert-Warshauer and just write GV. And the GV bound says that the code size, okay, so perhaps I need to make that a little bit clearer. The maximum possible size M of a binary code of length n and minimum distance d satisfies the equation M is sorry, I need a lower bound, so I need the inequality to go in the opposite direction. So, M is greater than or equal to 2 to the n divided by the sum I goes from 0, and at this point you must be thinking this looks just like the Hamming bound. Well, it does, but there are two differences. One is of course that it is a lower bound, not an upper bound, and secondly, whereas earlier in the case of the Hamming bound you would have a t here, 0 to t, you have 0 to d minus 1. So, those are the two differences. So, how do you prove this? So, the proof is via a greedy algorithm for code construction. So, it proceeds like this. What we do is we take a code word. So, we are building up a code by picking code words one at a time, and of course, we have to keep in mind that our code must have block length n and minimum distance d. So, we have to keep this parameter d in mind as we go along. So, you would begin like this, pick any vector at random. Okay. Let us just pick any vector here and let us make that our first code word. Now, because you want minimum distance d in your code, you are forced, you cannot pick another code word which belongs to a ball of radius d minus 1 around this code word. So, you say okay, that is fine. So, you draw this ball and the radius of this ball is d minus 1, and so when you pick your next code word you say okay, I must avoid this ball. So, in fact, what you do is from the set of all n tuples, which is f2 sup n, you throw out all the vectors in this ball after picking your first code vector, and you throw out the code vector too. You do not want to pick the same code vector twice. Then you pick another vector. So, let us say you pick your next code vector, and that is somewhere here, that is 2. Similarly, there is a ball of radius d minus 1 surrounding that. So, you pick the code word, then throw out all the vectors in that ball, and then you pick your next vector, and that could be C3, and again what you do is you throw out all the vectors in a ball of radius d minus 1. Now there are a couple of subtle points about this algorithm. One is that now you see this intersection of circles and it bothers you and says, wait a minute, you are not supposed to have intersection, you are doing something wrong. There is nothing wrong with this, because these balls can have intersection. It is just that no two code words must be within having distance d of each other. So what you are doing is that whenever you pick a code word, you are always going to throw away all the vectors which lie in a ball of radius d minus 1 surrounding that code word. Now some of these may already have been thrown away, right, because if there was intersection, then these balls in these intersections would already have been thrown away, so you do not need to throw them away twice. So just keep that in mind. But certainly, regardless of that, it is certainly true that as long as m times the sum n choose I to 0 minus 1, as long as this is less than 2 to the n, we can always enlarge the code to size m plus 1 while maintaining a minimum distance of d. Okay. So again, just in case that was not clear, let us go back here. What we are saying is that it may be that you have thrown out less than sum n choose I through d minus 1, but we will assume the worst case. Okay. We will actually be pessimistic and assume that you have thrown out, that you had to throw out all of them, and even if you did that and still the number of vectors is less than 2 to the n, that means that somewhere lying in this box there is another code word that you can pick. So you can continue this process. Okay. Now this part you might want to just pay attention carefully. So the argument is that as long as this equation, so maybe I will call this equation 2, so call this equation 2. As long as equation 2 is satisfied, you can enlarge the code. Now at some point equation 2 will fail to be satisfied, and that is when you cannot enlarge the code any further. However, you are guaranteed to reach a point where this equation fails. Okay. So we will just simply say at the stopping point where this process cannot be continued, at the stopping point we will have m greater than or equal to 2 to the n divided by the sum and this is the Gilbert-Washama bound. Now I am referring to this as a greedy bound. Greedy I would interpret in the following way, that is that what you do is you do not look at long term consequences, you only look at short term consequences. Once you pick the code word, then your overriding concern is that the next code word you pick must be at least distance d away from it, and that is all that occupies your mind. So given that, you pick your next code word, okay, and so on. So it is a short term viewpoint algorithm and it produces a code of this guaranteed size. Now, I have given you the Hamming bound and the Gilbert-Washam bound. So, this is the Gilbert-Washam bound, and very early we looked at the Hamming bound. Now, what we will do next is that examine the same two bounds, except that we look at them as if n were very, very big. We look at very, very long codes. So that's going to lead to some calculations. So now you'll ask, okay, why are you interested in long codes? I mean, if isn't a short code good enough? And I'll try to interest you in long codes by giving you a long code approach to achieving reliable communication. Okay, and I'll explain what I mean by that. So, I'll call this an approach to attaining reliable communication. Now, this approach has two features. One is it employs, so let me perhaps let me put down features here. So, features: 1, long codes are employed. Long codes meaning codes of long block length. Second, you assume bounded distance decoding. So, just to make the second point clear, let us put down a formal definition of this bounded distance decoding. Definition: a bounded distance decoder is one which, when given a received, so I am also going to draw a picture here in the middle of this definition, just to make things clearer. And T is going to be D minus 1 upon 2 as always. So, when given a received vector y examines the ball B y t, which I have shown above, and declares C hat, which is the decoded code word, if C hat declares C hat to equal C if C is the only code word in the ball. Okay. Else gives up. Okay, that gives up, else gives up is parenthesis. It's not very interesting, but what is interesting is what it does when it finds out that within this ball there is a single code vector C. Now, of course, if there are two code words, then of course it won't know what to do. Sorry, actually I take that back. It's not possible that there are two code words. Yeah, that's simply not possible, because then the Hamming distance between the two code words would be no larger than 2t, which is less than the minimum distance. So what could happen is there could be no code word within this ball, in which case it just gives up. So such a decoder is called a bounded distance decoder. Now you might say, well, what else is there? I mean, what other kinds of decoders are there? This sounds very logical to me. So what an alternative decoder might do this, and we'll actually be coming to this soon. An alternative would be to do the following. Instead of, what it might do is it might just partition the set of all n tuples. So let's say that this is f2 to the n into regions and say that, look, if the received vector is in here, I am going to decode C1 and so on. So it's going to partition the region, and then to every region it's like a territory, and if your received vector, let's say, happens to fall in here, then you simply decide decode C8. So these decision regions are based on Hamming distance, as you might expect, but the difference is that earlier you would only confine yourself to looking in a ball of radius t around the received vector, whereas here you are actually saying, look, I am just going to look for the nearest code word and I am going to decode to it. In a way it is a simpler philosophy, and as you will see, the better one. But the bounded distance decoder decoding applies in many situations, for reasons I think which will become clearer a little later. Okay. So hopefully you are clear about what a bounded distance decoder does. So we are going to now therefore look at an approach to making communication reliable by using long codes and employing this bounded distance decoding algorithm. Now there is this word reliable. What do you mean by reliable? So this actually goes back to Shannon. So what we mean by reliable communication is communication in which the probability of error is negligible. Okay. So note, by reliable communication, we mean communication with negligible probability of error. You can also think of this as virtually being error free. So that's important. Okay. So we are not satisfied with making the probability of error small, we actually want to make it negligible, and it is not easy to do that, because and the reason why this is of interest is because Shannon tells us that it is possible. What he says is that, look, if you are trying to communicate across a communication channel, and it will always be the case that the channel is not perfect, it is going to introduce some distortion, and he says the distortion on the channel does not prevent you from achieving reliable communication. The only thing that it actually does is that it limits the maximum rate at which you can communicate. Okay. All right. So, what then is our approach? So, we started off by saying we have an approach towards attaining reliable communication. It is going to use long codes, and that is why we are interested in the Hamming bounds for large n. So, our approach is this. Okay. We are going to say that consider the binary symmetric channel. So, the input 0 1, output is 0 1, and the crossover probability is epsilon. When, and what we are going to do is, across this channel, we are going to send a code word, and what is going to come out of this is a received vector y. Now, this code has large block length n. So, we are going to send therefore n symbols across the channel, and the binary symmetric channel is going to corrupt some of those code words. Okay. So, the probability that k code symbols are corrupted is given by n choose k, epsilon to the k, 1 minus epsilon to the n minus k, and we know that. Now, this comes from the binomial distribution. It is well known that when n is large, this distribution tends towards the Gaussian distribution. Tends to become Gaussian. And Gaussian with parameters so let us add that here, with parameters mean equals n times epsilon, and the standard deviation which is equal to the root n epsilon 1 minus epsilon. Okay. So, we have only about a minute left. So, just to summarize, what we have looked at is we have looked at bounds on the size of a code, we looked at the Hamming bound, then we talked about perfect codes, we talked about the Hamming code, the Golay code, then we looked at the Gilbert-Rashama bound, and now I am looking at trying to explain why is it that long codes are of interest from the point of view of attaining reliable communication. So, we will pick up on this in our next lecture. Thank you.